Hello, I'm Sina and I'm presenting my MPP project on intoxication detection from audio using deep learning. And my project advisor is Professor Emmanuel Agu. In the US, every day, 30 people die from motor vehicle crashes due to alcohol intoxication. Also, 44 billion of annual cost is from alcohol-related crashes. Intoxication tests, such as breathalyzers for evaluating safe motor vehicle driving, heavy equipment operation, and machine tool use require active user involvement and must be purchased and carried whenever drinking, thus reduce compliance. Passive detection of intoxication from voice has important applications to high-risk situations such as driving and steering. Alcohol is known to affect human behavior and can be dangerous when consumed in large amounts. Blood alcohol concentration between 0.05 and 0.08% are known to impair judgment. Higher concentration affects a person's speech, causing it to become slower, increase the number of pauses, stutters, and speech errors. This figure shows the difference between an intoxicated and sober audio sample. In this project, we use voice analytics to detect changes in speech patterns of an intoxicated speaker versus sober. There are two approaches that we can use using machine learning algorithms and deep learning architectures. Machine learning performs classification, taking hand-extracted features as inputs. Deep learning, however, performs additional feature extraction as well as classification. Majority of previous work uses classic machine learning approaches such as hidden Markov model, Gaussian mixture model, and support vector machines. We explore deep learning architectures to perform feature extraction in addition to hand-extracted features and ultimately improve the detection. We use the alcohol language corpus or the ALC dataset, which includes sober and intoxicated German speech recordings of 162 males and females in an automotive environment. Speakers are of different genders, ages, and speaking styles. This data is not balanced and includes 80% sober and 20% intoxicated audio samples. An unbalanced dataset where there are not equal number of instances for each class affects model performance negatively. We address this problem by applying three techniques. Figure 1 shows the original audio sample. Noise adds a vector of random noise to the audio sample, which is shown in Figure 2. The shift method shifts the audio sample forward by one time step, shown in Figure 3. And the stretch method stretches the audio sample by either speeding it or slowing it down at a fixed rate. And that one is shown in Figure 4. We use different methods to hand extract one-dimensional and two-dimensional features, which include MFCC, prosodic chroma, scaleogram, and log-mel spectrogram. We also use different evaluation metrics for our experiments. The two important metrics are recall, which is the number of true positives over total actual positives, and unweighted average recall, which is the mean of the recall scores for all the classes. Our architecture, for our architecture, we use three approaches: an RNN-based option, a combination of CNN and RNN, and a CNN-based architecture. RNN is a neural network architecture that remembers the past and makes the future decisions based on the knowledge it has. It's useful for sequences of data. Additionally, attention mechanisms have been useful for speech classification architectures. The attention mechanism consists of a feed-forward layer, which computes a vector of weights over the input audio sequence at a given time step. This table shows all of our experiments with the RNN-based networks. We use different augmentation and feature extraction methods. And for the architecture, we combine BiLSDM specifically with attention and pooling layers. The best result uses shift, MFCC, BiLSDM plus attention layer, and decision level max pooling. A convolutional neural network, or CNN, is a deep learning algorithm that takes images as its input. Voice analytics methods can convert inputs to spectrograms, which is an image, that are then passed into a CNN. In this architecture, we use CNN as an additional feature extractor to logMAL spectrogram for high-level descriptors, and RNN is used for classification. After post-processing the output features of the CNN into equal length 128-dimensional feature vectors, the features are fed into a BiLSTM model with attention and pooling layers. In this table, you can see different augmentation methods applied to the data, and features was passed into VGGish with different pooling layers. The classification network is taken from our RNN-based experiments, and we call it BiLSTM attention for simplicity. Our third architecture uses a CNN-based network and different pooling methods. We use state-of-the-art CNN algorithms that are presented in the next slide. This method gives us the best result out of the three approaches and was chosen as our proposed architecture. This table shows the result of using different pre-trained CNNs, including VGG16 and ResNext50 for classification. The VGG-ish model was also used in our experiments for comparison because it performed very well on the Google audio set data. Finally, this table shows our CNN experiments with VGG-ish and ResNext50 using different augmentation, different pooling, and attention methods. Some of the conclusions is that the best result from the last table that we just saw is that it's using ResNext50 model, decision pooling, plus feature level attention. The model achieved a UAR of 59.2%. This result is 9.2% higher than the results from standalone VGGish and ResNext50 pooling methods. Future work includes exploring a multi-class classification with audio samples split into different classes based on the BAC level. And we did not change the sampling rate of the audio we were using, keeping it at 44.1 kilohertz. Perhaps a lower sampling rate could help the model learn by providing lower dimensional audio input without discarding too much information in the audio. That was my presentation. Thank you for watching it.